In this video, we're going to talk about how to find when two different bank accounts with two different initial values and two different compounding periods and two different rates are equal. Basically, we're looking to find when two exponential functions are equal to each other. This technique will work for any two exponential functions. We're going to do it algebraically, and then we'll talk about using the graphing calculator. Now, what we're going to need to do first is get an equation for each. So one of them is going to be a bank account that has $1,000 at 5% compounded quarterly. Now, we're going to use this formula, B equals P times 1 plus R over N to the NT, where B is balance, P is principal, R is the rate as a decimal, N is the number of compounding periods, so we use that twice, and T is the number of years. So if we want to do one for $1,000, so that's our principal, or our initial value, and it's going in an account paying 5% compounded quarterly. So 0.05, because we need to change our rate to a decimal. Quarterly is 4 times per year, so N will be 4 to the 4t. So there's our bank account or balance for the first account. The second will be similar, but notice it's actually being compounded continuously. Continuously, we have a little bit different formula, sometimes called the PERT formula. It's B equals PE to the RT. Looks like it spells PERT. So for our second account, our initial amount is $700 times E, that'll always be in the compounded continuously, raised to the rate, 0.06t. So we don't need to worry about the number of compounding periods. Now let's talk about how we can solve this algebraically. Well, we're looking for where the two bank accounts are equal. So we're looking for where our account number 1 times 1 plus 0.05 over 4 to the 4t equals 700 e to the 0.06t. So, we need to solve this equation for t. Again, I'll show you how to do it in the graphing calculator afterwards, but I want to show you how to do it algebraically as well. First thing we're going to do is we need to divide by one of these factors out front. Since they're not the same, we're not going to get rid of both. We're going to have one. But we can at least get rid of one of them, so I'm going to divide both sides by 700. And at least I isolate one of my exponentials. And here we can cancel out 2 of those, and we're going to get 10/7. So I have 10 over 7 times 1 plus 0.05 over 4 to the 4t equals e to the 0.06t. So now we're going to go and we're going to use logs to help us simplify so that we can get a little bit nicer numbers to deal with. And we can simplify what's inside these parentheses as well. So what I'm going to do, let me move this over a little bit, is because I have this exponential isolated, I'm going to do a natural log of both sides. Now we could rewrite this problem using logs, but I sometimes think it's easier in this situation to just take a natural log of each side. The reason is this right-hand side, by properties of logs, natural log of e to the 0.06t is just 0.06 times t. And we got it solved there on the right-hand side. Now on the left-hand side, it's not quite so straightforward. We cannot pull the 4t out front right now because 10/7 is not raised to the 4t. We're going to have to use a property of logs. In fact, the property of logs for multiplication, which says it turns into addition. So we have natural log of 10/7 plus natural log of 1.0125 to the 4t, and that's equal to the 0.06t. Now this exponent can be pulled out front. So we have natural log 10/7 plus 4t natural log of 1.01 0.25 equals 0.06t. Now, we need to solve this guy for t. I have two terms with a t in it. So to do this, I'm going to need to get those two terms on the same side. So we're going to do that with some subtraction. In fact, I'm going to move everything over to move this guy over to the left-hand side. So what I'm going to have is natural log of 10/7 equals 0.06t minus 4t natural log of 1.0125. Alright, the reason we do that is because now a t can be factored out of this right hand side. I can rewrite this right hand side as t times 0.06 minus 4 ln of 1.0125. So what I've done is I've factored the t out, and that's equal to ln of 10/7. So to finish solving for t, all I need to do is divide. Just a parenthesis there. So t is equal to natural log of 10/7 all over 0.06 minus 4 ln of 1.0125. And notice I can actually use a straight equals because this is the exact answer. Now, if you return this answer and all we're looking for is the number of years for these accounts to be equal, somebody's probably going to give you an odd look. So we should know how to calculate these. So let's first see how we can calculate this, and then we'll see how we could have done it graphically from the beginning. So we're going to separate our numerator and our denominator with a set of parentheses. And in the numerator, I'm going to have natural log of 10 divided by 7. And my numerator divided by, now definitely a set of parentheses for the denominator. 0.06 minus, sorry, my minus key sticks, 4 natural log of 1.0125. Close up set of parentheses for the natural log, close it for the denominator, and I've got that it's going to take about 34.595 years, because t is in years. Okay, now that's how we could do it algebraically. Let's talk about how we could do it straight from the beginning. So what I want to go back to are our two equations, and let's see how our answers match up. What we're going to do is in our y equals, we'll clear out anything that's in there, and we're going to put each of those in as a graph. So I'm going to put 1000 times 1 plus 0.05 divided by 4 raised to the x. So let me... Okay, now I'm also going to put 700 second e to the 0.06x. So you can take a look at that, see how I have them in there. Okay. Now what we want to do is we want to find where these are equal, so we need to find where they intersect. So we're going to do second calculate. Intersect is number 5 there. We've done this a few times in some of my other videos. But maybe we should make sure we see our graphs first, huh? So I'm not seeing my graphs right now. Let's actually start off in a standard window. Sorry, having a little graphing calculator issue here. Alright, so if we start off in a standard window, we don't see our functions. Well, notice one had a starting value of 700, the other had a starting value of 1000, so I'm definitely not going to see them. So we need to pick a window that makes sense for our functions. So we need our y-max to be at least 1000, so let's go up to 2000. And our x-max, well, we know what it's supposed to be, but let's say we didn't know ahead of time. Well, it's going to probably take more than 10 years for that one to catch up, so let's try 30 years. And let's just see what we see. So here comes our first one. And notice it's right in the middle, so this is the one with the initial value of 1,000. And so after this will come our continuously. And to see where these two intersect, we do second calculate intersect. Are you fucking